Okay, welcome to today's lecture. So in the last class, what we looked at is the serial manipulator, which was 2 degrees of freedom, and it was actuated by two revolute joints, which were actuated by two of servo motors. Today we'll proceed and look at a parallel manipulator. Now this is a parallel manipulator, which is a 5 bar. Basically the base link is fixed, which we say the link which is a fixed base, and then there are the other links which move around. So this is a parallel 5 bar mechanism, which we'll be seeing today. And after that, we'll be looking at the mobile robot. So we'll do some experiments with a mobile robot, for example, obstacle avoidance, following a line, and the basic fundamentals of how to develop a mobile robot and how to use it. So first, as usual, I will be looking at the manual and explaining what we're going to do today, and then we'll proceed to the experiments. Okay, so this is the first experiment today, which is the kinematics of a 5 bar parallel manipulator system. Now in the last class we looked at a manipulator which was essentially consisted of 2 degrees of freedom, which was a serial manipulator. This one is a 5 bar, and as usual what we'll do is we'll first fix the manipulator, which I will explain here as shown in the figure here. So what we are seeing is that the manipulator has to be first fixed on the graph paper. That is basically I want to fix my 0, point of the base of the manipulator, which is marked here with the x-axis and the y-axis. So that is my 0 point. And now something to note here is that this is a 5 bar. So which are the 5 bars? The base is considered to be the fixed link, which is considered the first one. Then we have second, third, fourth, and fifth, which makes it the 5 bar mechanism. Okay, you would have studied about 4 bar mechanisms also, but this is a 5 bar mechanism. Now, if you look at the base as shown in the figure on the right, then what we see here is that the way the angles are defined, and you can see the position of the x-axis and the y-axis, and the 0 marked just in between the two revolute joints. And on the left hand side you can see the positives. So what it means is that anti-clockwise direction is taken as positive and clockwise direction is taken as negative. So theta 1 is shown as positive here, and theta 2 is shown as negative in this case. So by changing theta 1 and theta 2, we can get the tip of the end effector of the 5 bar mechanism to go at position at some point in the graph paper. Okay, so what are the tasks for today? The first task for today is the forward kinematics. That is, we will explain that if you give theta 1 and theta 2 as input, the end effector, which is having a pen, will go and mark at some position. Okay, that's the forward kinematics. The second is visualization of the robot motion, in which case we are going to basically switch off the torques at the joints and we'll manually move the end effector to some position. Okay, and then we can draw figures or we can draw straight lines and curves, and the robot will play back that exact figure. So it is something like manually teaching. And the third we'll do today is trajectory planning. That is, if you want to follow a straight line or a curve, how can you follow a straight line by the end effector of this mechanism? So the first experiment for today is the forward kinematics. Now this is what we mean by a 5 bar mechanism. Now the forward kinematics of the 5 bar is a little bit more involved as compared to a 2 degree of freedom serial manipulator, essentially because you see here that if you look at the point P and P dashed, you can see that for the same theta 1 and theta 2, they can have two positions. P and P dash can have two solutions. Okay, now how do you do the forward kinematics of this system is you might have studied in case of 4 bar mechanisms also. So what we basically do is we write the loop closure equation and then try and solve it. Okay, so in this case we will not do the loop closure equation here in this course because it is a little bit more involved. What we'll do here is that we have developed a simulator in Python. So what we'll do, not Python, but we're going to use the physics engine, which is the MuJoCo simulator already, which is there. Now this is an open source physics engine. So what we'll do is we have developed the kinematic model in MuJoCo. What we'll do is we'll change theta 1 and theta 2 and see how that point P is moving in space. Okay, that's what we mean by the forward kinematics. So the simulator looks something like this to correlate both of them. So you can see that the red line on the top figure, which is the base of the 5 bar mechanism, which is not moving, is the blue color cylinder which is marked, and then there are two actuators. So we can develop this kind of simulation using a physics engine by looking at or joining the various links by means of joints. Okay, so in this case you can see that these are pin joints, and at the end there is an end effector which is a pen which is marked there. So when I change theta 1 and theta 2, what will happen in this simulator? The position of the pen is going to change, and that is what we are seeing in our first task, which is the forward kinematics of this. Now, if you want to develop the forward kinematics equation, you have to write the closed loop equation and then solve it, and which is also not very difficult. It can be done. Okay, maybe you can try it. So this is the first one. The second is now also to mention that when you're changing theta 1 and theta 2, the simulator will actually move to the position. This is what the simulator looks like. Okay, so this is what the MuJoCo simulator looks like for the 5-bar mechanism. So you can see in the GUI that there is a joint-based joint and there is control. And if you click on control, what you see here is the motor position left, motor position right. So if you enter the numerical values in radians of motor position left and motor position right, it will compute the forward kinematics and take the pen to a particular location. Okay, so that is the first one. So left motor angle in radians, right motor angle in radians, and then the MuJoCo simulator will compute the coordinates of the xy of the end effector. Okay, so that's the first part of the experiment. The second part of the experiment is visualizing the robot motion. So what we do is we run the program which will disengage the motors of the manipulator. So there are two motors which you can see here at the base. And if you disengage the torques of the motors, you can move the manipulator by hand. So as is shown here, the person can move the end effector and draw a star. So when it is drawing a star, you can record those points which it is covering by straight lines, and then can play back that device. The device can play back exactly the same trajectory that has been taught. So this is the second experiment. And in the third experiment is trajectory planning. So we'll plan very simple trajectories like straight line or a curve by giving the endpoints and then fitting a cubic polynomial which will take the end effector from one point to another point. Okay, so these are the three experiments for today. Okay, so let's start off by looking at the program. So the first program, the first one is here, in which case it is doing the forward kinematics of the program. And what we'll do is let us run the program. So it is connecting to your the simulation. You can see this is the MuJoCo simulation, and let me take it this side. So in terms of joints, in terms of control of the motor position, what I can do is, okay, so this is the 5-bar mechanism that we talked about. So what we are seeing is that this is the 5-bar where we are having the 5 bars of the mechanism. The base link which we say which is fixed is shown here. So this is the fixed link. This is one servo motor, this is another servo motor, and these are the 5 bars. This is the first bar which is fixed here. Then we have this is number 2, then this is number 3, that's number 4, and that's number 5. That's how it's a 5-bar. Now you can see that this is the end effector which is mounted onto the tip of the 5-bar mechanism. Now in a 4-bar mechanism, what happens is there is one more link here. Okay, and these two are fixed. That's a 4-bar mechanism, in which case this becomes a coupler. Okay, so that is the difference between a 4-bar and a 5-bar. Okay, so we are running the experiment now, and what we are seeing is that for different angles, what we will do is we will enter different angles here. So you can see that the angles in the simulator is changing, and when the angle in the simulator is changing, you can see that this is also moving and this is moving to different positions. Okay, so that is one position where it has marked. Now as we keep changing the angles, it will move to different positions, and the pen comes down and it marks the corresponding point. Okay. So this is the first part of the experiment, which is the 4-bar, sorry, this is the 5-bar and the forward kinematics of that. By changing the various angles, we are able to change the position of the end effector. Okay. Now there will be two solutions, as I was saying. One solution is this side. The other solution is the inverse of that, which is on the other side. So there is one more solution on this side. So this is considering only one solution, which is at the front side. So in the simulator, when we are changing the angles, this will change the position of the end effector. Okay. That's how we are controlling it, which is the forward kinematics of this. So by giving different joint angles, you can make it go to different positions. Okay. So this is the first part of the experiment. Okay, this is the second task that we are doing. So in this particular case, we are going to switch off the torques of the motor. So what that means is that the motors are going to become free, and then we can actually move the manipulator by hand. And when we are moving the manipulator by hand, it will be replicated in the simulation also. So what should we do? Straight line motion. Okay, so we are basically moving the manipulator by hand to some location. Okay, so maybe we are locating it there, and you can see automatically in the here also, if you have noted that this has also changed the position. Okay, so if I manipulate, if I'm going to move, so let me, you can see both maybe. I'm moving the manipulator by hand, or I'm holding it this side and moving by hand, and this is also moving as the manipulator is moving. You can see I'm moving the manipulator, catching it by hand and moving it. And what is happening, even in the simulation, it is moving. It is replicating the simulation. Okay, so what we'll do is, this is some kind of teaching. So here we have brought it to this position, and then we can store this position. Okay, this is the second task that we are doing. So in this particular case, we are going to switch off the torques of the motor. So what that means is that the motors are going to become free, and then we can actually move the manipulator by hand. And when we are moving the manipulator by hand, it will be replicated in the simulation also. So what should we do? Straight line motion. Okay, so we are basically moving the manipulator by hand to some location. Okay, so maybe we are locating it there, and you can see automatically in the here also, if you have noted that this has also changed the position. Okay, so if I manipulate, if I am going to move, so let me, you can see both maybe. I'm moving the manipulator by hand, or I'm holding it this side and moving by hand, and this is also moving as the manipulator is moving. You can see I'm moving the manipulator, catching it by hand and moving it. And what is happening, even in the simulation, it is moving. It is replicating the simulation. Okay, so what we'll do is, this is some kind of teaching. So here we have brought it to this position, and then we can store this position. Okay, so it has come down and it has marked. Okay, then I can move it and follow this trajectory. For example, I'm following this trajectory. So that is something like a, okay, so that is the trajectory that we have manually taught it now. Okay, so you can see that in the simulation also, it has drawn exactly that same trajectory. Okay, so this is basically one way of teaching. And when it is moving the actual robot, you can see both of them here. The actual robot has also moved, and the simulation also has copied exactly the same motion. So you can copy some other kind of trajectory. For example, we draw any kind of shape. Okay, and exactly the same shape is going to be replicated on the simulation also. So there is feedback from the motors which is coming, and you can see that if you see it more closely, exactly the same shape has been drawn there also. Okay, so this is a task for tracking, in which case we can move the manipulator is doing exactly the same thing, and in the simulation it is showing that only. Okay. Okay, so the third experiment is drawing the line segments, where we can give the start point, end point. Okay, so for example, as shown here, and what it will do is, it is going to follow the exact, it is going to draw the line segment. Or you can also draw curves by giving it cubic polynomials. So there are different kind of curves, straight lines which can be drawn, and we can teach this, not teach it, we can give the start point, end point, and what it will do is, essentially it is going to follow the same thing in the real world. Okay, so first let's draw a straight line. So that too very fast, maybe you can draw it again. Okay, so that drew a straight line. You can see that it's almost a straight line. It just drew the straight line here. So the third experiment is drawing the line segments, where we can give the start point, end point. Okay, so for example, as shown here, and what it will do is, it is going to follow the exact, it is going to draw the line segment. Or you can also draw curves by giving it cubic polynomials. So there are different kind of curves, straight lines which can be drawn, and we can not teach it, we can give the start point, end point, and what it will do is essentially it is going to follow the same thing in the real world. Okay, so first let's draw a straight line. Oh, that too very fast, maybe you can draw it again. Okay, so that drew a straight line. You can see that it's almost a straight line. It just drew the straight line here. What about a curve? So can we draw a curve also?
Yes.
This is similar to a figure of 8, but it's not very accurate, you can see, because of the stepper motors are not very accurate. Okay, so you can draw different kind of figures this way. Okay, so what we saw is a parallel robot, that is a 5-bar mechanism. Now the control of that is a little bit, or the forward kinematics is a little bit more involved than a 2 degree of freedom serial manipulator. Okay, so the next experiment that we are going to have now is the mobile robot. Now, in the case of the mobile robot and its applications, a mobile robot has 2 wheels. This is a differential drive robot. So there are 2 wheels. Let me show where is the figure of the robot. Yeah, so this is the figure of the robot. And what you can see is that it has a left wheel and a right wheel. And there is a third wheel in front, which is a caster wheel, which is basically a support wheel. Okay, so because the robot cannot support just on 2 wheels. So essentially there are 2 wheels which are driven by 2 motors, DC motors, which are driven by a power amplifier and then the Arduino microcontroller. And then what you see is that by giving different velocities to the 2 wheels, the robot can move in different directions. So for example, the one that is the figure that is shown extremely on the left side, that is to go forward. So if both the velocities are in the forward direction, it will go forward. If both the velocities are in the backward direction, it will go back. Now, if the velocities are different, for example, the left velocities in the forward direction, the right velocities towards the rear direction, then it will rotate about a point. Now, in the extreme right, if you see if the left wheel velocity is on the rear side and the right wheel velocity is in the forward direction, it is going to revert, it is going to rotate in the anti-clockwise direction. Okay, so by giving different combinations of these velocities, you can make it move forward, turn back, then turn left, turn right, and rotate about a point. Okay, this is basically called a differential drive robot. Now, what are the experiments that we are going to do here is first we'll see the structure of the robot, that how the robot is made, how the robot is constructed or put together. Now this robot also has different kind of sensors. For example, it has an ultrasonic sensor which is in front, okay, and then it has infrared sensors which are at the bottom. So what we'll see is the robot that is going to move along the robot which can avoid obstacles because of the ultrasonic sensor which is in front. Okay, so if it sees an obstacle in front, what will happen? It will change its direction. Now, in the case of a line following robot, at the rear side of the robot, there are ultrasonic sensors. Sorry, not ultrasonic sensors, but infrared sensors. So these infrared sensors can sense light. So when it is following a black line, for example, 3 of the sensors are going to sense the surface condition. So for example, if there's a black line, so one of the sensors will be showing white, then black, then white. Okay, so in terms of the signal, it could be 101 or 010. And basically by following that, the robot can actually follow the line. Okay, so these are the 3 experiments that we have. This is the line following that I was talking about. So in this line following robot, there are 3 IR sensors at the bottom, and it will try and keep the sensor on the bottom, in the middle rather, on top of the line. Okay, so it will keep the left sensor on the left side of the line, the right sensor on the right side of the line, and the central sensor on the line. And this is how it is going to follow a straight line. Okay. So this is the experiments, 3 experiments. One is basically to look at the working of the ultrasonics of the mobile robot. That is, it has to go front, it can go back, it can turn left, it can turn right. The second experiment is by using the ultrasonic sensor just to avoid obstacles. Whenever there is an obstacle in front, it changes its direction. The third is line following using IR infrared sensors. So whenever the sensor is on the line, it tries to follow the line by looking at the logic. Okay, so let's look at the program and then let's look at the actual experiment. Okay, this is the mobile robot we are talking about. So you can look at the construction of the mobile robot. Let me explain. So at the bottom there are these wheels. Okay, so there are wheels here. This is one wheel, this is another wheel. Okay, you can see the 2 wheels. These are connected by small DC motors. There's one DC motor there and there's a DC motor there. And these 2 DC motors are driven by a line by a power amplifier, which is at the top of the. And this is the caster wheel I was talking about. So this is the support wheel of the caster wheel, which is basically a ball, and it's just for support. So it doesn't have any function but just to support. Now, depending on the 2 velocities, angular velocities of the 2 wheels, the robot can go straight, it can go back, then it can turn left, it can turn right, simply by changing the wheel velocities. Okay. Now, this is the infrared sensors I was talking about at the rear side. So these are the infrared sensors. You would have done experiments in this infrared. So one is an emitter and the other is a receiver. Okay, so there are 3 of them here. In the case of the line following, as shown here, so you can understand that very easily. So there are 3 sensors. If the central sensor is lying on the line, so let me look at it like this. So the central sensor, when it is on the line, this sensor is outside, it's on the white area, that other sensor is also in the white area. Okay, so it basically understands that one of them is on the black line, and that's what it tries to do. So if the robot were to go towards the left side, for example, like that, what is happening is the rightmost sensor now is on the black line. Okay, and the other 2 sensors have gone on the white line. So it basically understands logically that it has to turn on this side now and bring it in that configuration. Okay, and if both of them have gone out this way, then again it knows it has to turn that way and bring the central sensor on that line. So the logic is to ensure that one of the sensors is on the line, on the black line, the other 2 sensors on the sides are on the white line, white area I mean. Okay, so that is one. The second is if you look at the inside of the robot, these are the batteries, and this is the Arduino microcontroller which is there, and in front of the robot there is an ultrasonic sensor. So this is an ultrasonic sensor, one is an emitter and the other is a receiver, and the ultrasonic sensor is connected to a servo motor. That's a servo motor, and this is basically, it can rotate about a particular axis. Okay, so if it sees something in front, what it does is it rotates towards the left, then it rotates towards the right. Okay, and to see where, if there is something in front, and if there is something in front, it will immediately see the direction in which there is no obstacle in front. Okay, and move in that direction. Okay, so that is also the second experiment that we have. The third experiment is the line follower robot, the line follower. Okay, so this is the internal construction. You can see it's very simple. You can make it by yourself. And okay, so the first experiment is robot going right, going straight, going back. So let us put it here. The robot is put here. Okay, so this is another robot. So this is the robot going towards the right. So going front, going, let us bring it in the center. Here. So these are the various motions of the robot. You can see it can turn. Okay. So simply by changing the wheel, so simply by changing the angular velocity of the wheel, it can go in different directions. Okay, front, back, left, right. Okay, so that is basically to show how the robot actually can go at any point in the workspace simply by changing its wheel velocities. Okay, this is a differential drive robot. Okay, so this is the first experiment where we saw that the robot can go in any direction. Now, in terms of controllability, this is a fully controllable system, which means that the robot can actually go and park anywhere. Okay, although it's a non-holonomic system because the robot cannot go sideways, but it can still go and park anywhere using a combination of different motions. Okay. Okay, so our next experiment is the obstacle avoidance. So this is the robot which just has an IR sensor in front. So suppose I put my hand in front, you can see what it is doing. It is seeing the direction in which there is nothing in front, and it will go in that direction. So let me put my hand again. Okay. So this is the obstacle avoidance. So what it does is it basically sees if there is an obstacle in front and then finds out which direction there is no obstacle and goes in that direction. This is also a very simple experiment which actually gives the idea of obstacle avoidance by mobile robots, autonomous cars. Okay, this is the third experiment, that is the line following robot. Okay, so as I was explaining that there are 3 IR sensors at the bottom, and this is the line follower. It looks like a racetrack, you can see. So what it is doing is it is basically, let me see the bottom of the robot. You can actually see the IR sensors going, the red light that is coming off. Okay, so what it is doing, it is trying to keep one of the sensors, the middle sensor, on the black line. Okay, it has reached the stop point. So that is the stop point where all the 3 sensors become black. Okay, so we can bring it again and start it from this side. Okay. So it is finding the stop point and goes and stops in the stop point. It is shaking, and you can guess why it is shaking, because what it is doing, whenever the sensor goes off the line, it tends, especially in the curves, it tends to bring the robot back by very, very small motions. Again, it is coming very close to the stop point, and once it reaches the stop point, it stops there. Okay, so you can see that all the 3 sensors are right on top of the black line there. Okay, so today we looked at 2 simple experiments. One was the 5-bar mechanism, which is our planar robot, and the robot is used extensively for this robot is having a little different kinematics, but is also very interesting to understand the kinematics of a closed loop chain like a 5-bar mechanism. And after that, we looked at, we also, in the 5-bar robot, we also looked at MuJoCo simulation, where you can develop very simple, using physics engines, you can develop by using different kind of linkages and joints, you can make robots, and you can do forward kinematics, inverse kinematics, and simulations. And after that, we looked at the mobile robot. Now, the mobile robot is a very simple robot using just 2 actuators with a caster wheel for support. And we can understand the basic principles of how a mobile robot moves, how it goes forward, backward, how it turns. And we looked at 3 applications of the robot going in different positions. And then we looked at the application of obstacle avoidance using ultrasonic sensor in front. And the last one was using an IR sensor. So the infrared sensor can be used for applications like line following, going to some stop point. Okay, so we'll stop today.